going to log in on the computer. Okay, fine.
Oh, okay, great.
Today our guest is Professor Valentino Tossati, and as you can see from the screen, he's going to talk about currents with minimal singularities and F11 classes. Please.
Okay, great. Thank you so much for the invitation. So yes, what I will talk about is I wrote is a work in progress with Simeon Philip. Actually, yes, there will be, eventually I will explain what we are doing right now, but I will probably give a more broader overview of certain questions that we have been thinking about in the recent years. So the focus, I guess, will not be on this too much on the recent result, but more to give a picture and hopefully enough problems that we don't know the answer to. So, so this is a talk about one-on-one cohomology classes. I will also give some motivation in the next slide. So in all the talk, I will fix X Kummer K3 manifold, although for some of these definitions, maybe most of them, the Kähler is not actually needed. So you can also extend some of these concepts to just Kummer complex manifolds, replacing Kähler metrics by Hermitian metrics. But because of all the applications in this talk will need Kähler, I will just assume Kähler from the beginning to be safe. So n will be the complex dimension, and omega will be some fixed Kähler metric on X. And we will work with the H11 with real coefficients. So this can be interpreted in various ways. The easiest way to think about it for this talk is simply close the real 1-1 forms modulo IDD bar exact ones. So IDD bar phi, where phi is a smooth real valued function. And that's, of course, the same as DDC phi. So I just use IDD bar, but it's the same as DDC. And if alpha is one of these closed real 1-1 forms, I would denote by this bracket alpha the cohomology class in H11. This, of course, H11 is a finite dimensional vector space. And inside this finite dimensional vector space, you can define several cones, although maybe I won't refer to the cones directly. You can define various notions of what it means for the class to be positive or semi-positive in various ways. And usually the set of classes of these positive elements forms a cone. So the simplest one is the Kähler. So a class is Kähler if it contains a Kähler metric, which you can phrase by saying that there exists some epsilon positive and a smooth function phi such that alpha plus dd bar phi becomes strictly positive, so bigger than epsilon omega on the manifold. And so this is the simplest positive cone, the cone of Kähler classes that we can consider. And if one takes the closure of the positive cone, one obtains the second notion, which is called Neff, which says that for all epsilon positive, strictly positive, you can find a smooth function phi, which does depend on epsilon now, such that alpha plus dd bar phi epsilon is bigger than or equal to minus epsilon omega. So it's almost semi-positive. And yeah, as I said, it's a simple exercise to show that a class is Neff if and only if it's a limit of Kähler classes. So this is simply the closure of the previous condition. And a class is called obsef, which is a pseudo-effective if there is a function phi, which doesn't have to be smooth, it's only quasi-plurisubharmonic. So locally it's the sum of a smooth function plus a PSH function, such that it's actually alpha plurisubharmonic. So if I do alpha plus dd bar phi in the weak sense, I obtain a closed 1-1 current, and I want this closed 1-1 current to be positive, bigger or equal to 0. And alpha is called big if you can strengthen this semi-positivity to strict positivity. So if there is some, I mean, essentially the same definition as a Kähler, but phi instead of being smooth is just quasi-PSH. So there's a quasi-PSH function such that alpha plus d bar phi is bigger than or equal to epsilon omega. And again, one can put these together into cones, and it turns out that the pseudo-effective cone, again, is the closure of the big cone. And these four are quite standard in the subject. The next two, well, also the next one is also sort of standard, but a lot less studied. So we will say that alpha is semi-positive. It's actually a very natural definition, if you can find a smooth function phi such that alpha plus TD bar phi is semi-positive. So this would be the most naive weakening of the Kähler assumption with epsilon equal to 0. And then alpha is called, this is really non-standard. So if you want, I made up this definition, this name at least. We will say that alpha is semi-ample if the alpha is the pullback of a Kähler class under a holomorphic map from X to Y, which should be surjective and with connected fibers, and onto Y, which could be a Kähler manifold, but in fact, one can allow it to be a singular, let's say, normal Kähler analytic space. And omega Y is a Kähler metric on Y in the sense of analytic spaces. So maybe this is a bit annoying to digest at first. I will explain the motivation in the next slide. But let me just remark that if you have a holomorphic map to an analytic space Y, possibly singular, say, and you have a Kähler metric in the sense of analytic spaces, if you pull it back to X, so there is a pullback of smooth forms within analytic spaces, then the pullback to X is a smooth one-one form. And since omega Y is assumed to be strictly positive on the analytic space, the pullback will indeed be non-negative. So what I just explained is that one of these implications at the bottom of the slide. So if you have a class is Kähler, then the class is semi-ample. This is trivial. You just take X equals Y and omega Y to be your Kähler metric. And semi-ample implies semi-positive. This is what I just said. Semi-positive implies Nef is trivial. You can just take epsilon to be the one for epsilon equal to 0 works for all epsilon on negative. And the Nef implies pseudo-effective is not obvious from the definition, but it's semi-obvious from a simple consequence of weak compactness of currents. And on the other hand, Kähler also implies big, which is also obvious from the definition, and big also implies Psef, which is also obvious. So you have these implications between the various positivity notions, and none of these arrows can be reversed. So for any of these arrows, there are counterexamples that show that you cannot go back. That you cannot go back. Some of them are actually quite complicated to find. Okay, so yeah, so semi-ample may not be super standard. Let me explain where these come from. So these positivity notions, I forgot to say, right, that most of them were introduced by Desmailly. They are inspired by the analogous notions for line bundles. So if you have a holomorphic line bundle on X and H, you can fix a smooth Hermitian metric on L. And then you have the curvature form that I denote with the RH, which is locally given by minus IDD bar log H. So locally H is a smooth positive function, and globally it defines a closed real one-one form. And the Furtchen and the class of this in H11 is the Furtchen class of L, so C1 of L. So basically for every holomorphic line bundle, yeah, of course this class does not depend on the choice of the metric H. And for every holomorphic line bundle, you obtain in particular a one-one class. And the class that one obtains in this way is well known. It's the Néron-Severi group, NS, which is simply you take the H11 and you intersect it with the free part of H2 of XZ. So this requires a little explanation, right? So the H11 by definition embeds into H2 of XC, I mean H2 of XR if you want. And then H2 of XZ usually doesn't embed in H2 of XR, but the free part does. So then this intersection is done inside the H2 of XR. Yes, so I mean, okay, I should really put here complex coefficients, sorry, but I only care about the real part, so here. So the real Néron-Severi group, you just take the Néron-Severi group and you tensor by R over the integers. So the real Néron-Severi group is, let's say, if X is projective, is actually the space of numerical equivalence classes of R divisors. So NSX is the Furtchen classes of line bundles, and these can be thought of Furtchen classes of R divisors. So this means that H11 can be thought of as an enlargement of the space of numerical classes of line bundles or R divisors. And what De Mailly proved is that these positivity notions are compatible with the classical ones in algebraic geometry. So if assuming that X is projective, of course, and if you have a line bundle, then this is ample or Neff or big or pseudo-effective in the sense of algebraic geometry of any of these four, if or only if its first-rank class has the same property as defined in the previous slide. And the same holds for Q or R divisors as well. So these notions are at least these four ample, let me go back. The first four in this list are well behaved with respect to comparison with algebraic geometry. Now, the semi-positivity here does not correspond to any algebra geometric notion. So that's really somehow a transcendental condition that doesn't have any analog in algebraic geometry. And as for semi-ampleness, one has to be a little bit careful. So a line bundle L is called semi-ample. This is standard. If some positive power, say ML, is globally generated or free for some M. And now, once you have a globally generated line bundle, you can take an even higher power, perhaps, and sufficiently high, sufficiently divisible power, and you obtain a morphism. And this morphism is, the image is this normal projective variety Y. The morphism here is F. It has connected fibers. And you can write your line bundle as pullback of ample on Y, maybe modulo Q equivalent, because you have to take powers. So you see that, therefore, in this definition, I mimicked this property of semi-ample. So that means that L semi-ample implies C1 of L semi-ample, but one has to be slightly careful in the sense that you see these four properties, they're numerical, right? So this properties holds for a line bundle if and only if it holds for the first-rank class. Namely, it only depends on the first-rank class of L or the numerical class. But semi-ampleness is not numerical. So you can have two line bundles with the same first-rank class. One is semi-ample and one is not. For example, as in the password of this meeting, if you take an elliptic curve and you take a line bundle of degree 0, one which is torsion, one which is non-torsion. So, so the torsion one with semi-ample and the non-torsion one is not. Okay, so one can make it numerical by saying L is numerical equivalent to semi-ample, but that doesn't matter. So that hopefully explains all these notions. And there's also a relation with the singular metrics. So if you have a holomorphic line bundle L, H is a smooth metric and alpha, as usual, is the curvature. Then the representatives of the class of alpha, these are alpha plus TD bar phi by definition with phi smooth. Well, if you mod out constants, I mean, you can always add a constant to phi that doesn't change the TD bar. So modulo constants, these actually correspond bijectively to smooth Hermitian metrics on the line bundle L, simply by doing this H e to the minus phi. So given phi, you create this new metric. And of course, the curvature of this H phi is exactly alpha plus TD bar phi. So one can really think of representatives of these classes as, for a case of line bundle as smooth metrics on this line bundle. And then naturally, when phi is not smooth, but only quasi-PSH, we say following De Mailly that H phi is a singular metric. And the canonical example are these algebraic metrics where when you have a non-trivial number of global holomorphic sections of L, then you can form this function phi, which is log of the sum of squares using your metric H. And this indeed defines a singular metric, and alpha plus TD bar phi, alpha is the curvature of H, right? Alpha plus TD bar phi is semi-positive. So this is, of course, pseudo-effective C1 of L, and you have this algebraic singular metrics. Okay, and again, following De Mailly and Petten and Schneider, there is a notion of a comparison of singularities. So the point is, when you pass from smooth forms and smooth metrics to quasi-PSH functions and their closed positive currents and singular metrics, then quasi-PSH functions are always locally bounded above. So they don't go to plus infinity, but they can go to minus infinity, as for example, log mod z in one complex variable. And since they can go to minus infinity, those we think of as singularities. And so it's natural to say that if you have two alpha PSH functions where alpha is some fixed closed real one form, of course the class has to be pseudo effective so that you have you have some alpha PSH functions. Then we can say that one, say phi is less singular than psi if it's above, if phi is above psi up to a constant. So if there is any minus infinity locus, then psi goes to minus infinity faster than phi. So that in this sense has more singularity. And once you have this partial ordering, you can look at minimal singularities. So phi is said to have minimal singularities in its class. Phi, of course, is alpha PSH. If phi is less singular than psi for all alpha PSH functions psi. And in fact, it's surprisingly easy to see that these alpha PSH functions with minimal singularities always exist, although this probably was kind of a surprise back then. And for example, you could take this envelope or extremal function, which is the pointwise the soup of all, say, non-positive alpha PSH functions. Right? So this class psi here is not empty because alpha is pseudo-effective, and then you take the soup. And this, they prove always, I mean, it's almost tautological, has minimal singularities. And so of course, so you have at least one with minimal singularities, and then if you have another one, if phi and psi both have minimal singularities, then by definition, they're comparable. So phi and psi are comparable up to a constant. So we say that they have the same singularity type, and I will just call this phi min. So phi min will refer to any alpha PSH function with minimal singularities, and for any statements that I will make, the choice does not matter, as you will see. So I won't have to specify exactly which one it is. Okay, so the main theme of what I want to discuss is how singular is phi min. And what do I mean? Okay, let's look first of all at the stupidest observation, namely, if the class is semi-positive with my earlier definition, then you can take phi min to be simply the zero function, right? Because you can pick alpha to be semi-positive, so alpha plus zero is semi-positive already. So zero is a function with minimal singularities, and in particular, tautologically, the singularity type phi min is bounded. I mean, of course, it's just zero. So if you have a semi-positive class, every current with minimal singularities in the semi-positive class is bounded potentials, or the alpha PSH function with minimal singularities are bounded. On the other hand, here is an example where it's unbounded. I mean, very classical. If you just blow up a point on any manifold X, and E is the exceptional divisor, and alpha you take it to be the first-chain class of the line bound corresponding to the divisor E, then alpha is still effective, but in fact it contains a unique close positive current, which is the current of integration on the exceptional divisor. And if you fix a smooth metric on this line bundle, and alpha is the curvature, and you also fix a defining section of the exceptional divisor, then one has this Poincaré-Lelong formula that the current of integration on E is alpha plus dt bar of the log of the length squared. So it is indeed an algebraic metric with my previous definition. And as I said, it's the unique close positive current. So log of mod S square H is the unique alpha PSH function. It's the only one. And you can see that it's a log, so it is not bounded. It goes to minus infinity along E. Okay. And for the next slide, I will use a very coarse measure of singularities, which is the Lelong number. One of the possible definitions is simply to look at the strength of the logarithmic pole. So phi here is alpha PSH or quasi PSH. X is any point in your manifold. The Lelong number can be defined as the soup of all non-negative gamma, such that phi goes to minus infinity at least like gamma log z minus x near your point. So of course, if phi is bounded, then gamma is 0. So the long number is 0. So bounded quasi-PSH functions don't have long numbers. The converse is false, for example, by the standard double log singularity. And a simple computation, or simple enough, in the base book, is that if you take one of these algebraic metrics and you compute a long number, you get the multiplicity of the ideal generated by these sections. So it has a nice interpretation in terms of algebraic geometry. And so what are the long numbers of the current with minima singularities? So the first result in this direction follows from the Mazur regularization theorem for currents. So he showed as a corollary of that if alpha is a pseudo-effective class, and if current with minima singularities has non-long numbers everywhere, again, this condition does not depend on the choice of phi min. That's why this notation is allowed. So if you don't have any long numbers, then actually your class alpha is Neff. So you have this direction. So no long numbers for phi min implies the class must be Neff. So conversely, if the class is not Neff, then certainly you have some non-trivial logarithmic pose for the current with minima singularity, and therefore for all close positive currents in the class. And another extremely useful deep result of the main pawn is that if alpha is Neff, then you can decide if alpha is big simply by computing the self-intersection and looking if it's strictly positive. This is a natural generalization of asymptotic Riemann-Roch in algebraic geometry. So with this at hand, so it's very easy to check bigness. And then Sébastien Buxom, he proved that if alpha is Neff and big now, then indeed the current with minima singularity has no long numbers at all. Okay, so you see the gap. The first statement says if you have no long number, then you're Neff, and if you're Neff and big, then you have no long numbers. But the May-Paton and Schneider had earlier constructed examples, indeed on a ruled surface, ruled over an elliptic curve, where you have an F class which is not big, and there are some the long numbers for the current with minima singularity. So in this example, actually, is similar. I mean, the behavior is like in the blow up in the sense that this class has a unique close positive current, which is the current of integration on a hypersurface on a curve, and in particular, you have the long number at all the points on this curve. And I think Berman and Buxom were the first to notice that one can modify this example. Although I think later they moved it from their paper, and finally it appeared instead in Buxom ACDU Getch-Zeyahi later. So one can take essentially a cone over the previous example, and one can also find examples of alpha which is now Neff and big. So by Buxom, yeah, has no long numbers. But the current with minima singularity still is not bounded. It's not in L infinity. So this is just a small selection of these kind of results, and it shows to you that things can be quite subtle. And the main question, or kind of the thing one would like to understand, is if you're given an F class. So I assume an F simply because of the first step. Otherwise, you have some long numbers, and that cannot be bounded for sure. But so given an F class, how do we decide whether the current with minima singularity has bounded potentials? So if you want the alpha PSH function with minima singularities is bounded. And more restrictively, one can ask, how do we decide if alpha is semi-positive, or how do we decide if alpha is semi-ample? Remember, semi-ample was defined earlier in its non-standard way. It's the pullback of a Kähler class under some holomorphic map to some maybe singular analytic space, Kähler analytic space. So these are hard questions, and in general, but I would like to, so with Simi and Philip, we proposed the following conjecture, which, as you will see, is just another direct translation of the Kawamata's base point free theorem. So namely, if you have a Kummer K3 manifold X and a class which is Neff, alpha, and now you add this condition involving the canonical bundle, namely that lambda alpha minus kx should be Neff and big, for some lambda strictly positive. So if you have this condition, then we hope, the conjecture has three parts. The weakest conjecture claims that the curve with minimal singularities in the class alpha has boundary potentials. The stronger conjecture, intermediate stronger, says that even better, alpha should be semi-positive, which, as I said, implies the first. And the strongest form of all is that the alpha should be semi-ample. Maybe I should show it again. Semi-ample is non-standard. So we define this by simply imitating the semi-ample line bundle. So there should be a surjective holomorphic map with connected fibers onto a normal Kähler analytic space, and alpha is the pullback of a Kähler class on the analytic space, which implies semi-positive. So indeed, one can check that this condition does fail in all the examples on the previous slide. I mean, at least all the ones, all the explicit ones there's some ruling, there's some P1s or Pn inside, and that makes this quite negative, and that this condition is not satisfied. And this, as I said, is a direct translation of Kawamata's base point free theorem. So this would be the theorem where alpha is a line bundle now, X is projective, and you have a line bundle L, which is an F line bundle. And this condition simply says that M times L minus Kx is an FM big as a line bundle. Then Kawamata says that the line bundle is semi-ample. So in fact, Kawamata later was extended to R divisors by Hakon and McKernan, I believe. It's not that hard actually. So what this means is that the conjecture by algebraic geometry, the conjecture holds if the class is in the real Néron-Severi group. So it takes a second to see that if alpha is in the real Néron-Severi group, then actually there is an FM big. There is a big class which is in the Néron-Severi group. So X has to be projective automatically, and then you can apply Kawamata. So for classes in the Néron-Severi part, this is okay by algebraic geometry, and we are conjecturing the same, if you want, somewhat optimistically perhaps, conjecturing the same for all classes with the same conditions. And it's really, if you want, three conjectures. So as I said, C implies B implies A, so that one is stronger than the other. And notice that by scaling, I mean, the conclusions do not depend on the scaling. So you can always scale so that lambda is 1. And when lambda is 1, this condition alpha minus C1 Kx and FM big, you can say it means simply that alpha is the adjoint of an FM big class. So it's Kx plus an FM big class. So it's naturally a statement about, if you want, a statement about adjoint classes.
Sorry, could I ask about the signs here? Do you mean lambda alpha minus C1 of X or C1 of Kx?
Oh, did I flip it? I think it's C1 of Kx, right?
If you wanted Kx plus alpha for alpha being adjoint? Or?
Yeah. What I said is, alpha equals Kx plus beta, where beta is an FM big.
Ah, I see, okay.
Yeah.
Thanks.
Yes, yeah. Right. Yeah, it's correct. Yes, that's I know that the signs of C1 of X and C1 of Kx are inverted, and that creates a lot of confusion also to me sometimes. Yeah, this one is the right sign. Yes. Yeah. So alpha becomes the adjoint of a class which is an FM big. Yeah, thanks. So right, and also right, it's not hard to see that if you assume, if you want the statement C, namely if you assume that alpha is semi-ample and it satisfies this condition still, then if alpha is also big, see alpha is an F. If alpha is also big, then so semi-ample, as I said, means that alpha is the pullback of a Kähler class by a holomorphic map onto some Y. Then if alpha is big, this map will be bimeromorphic, if you want, birational in the algebraic category. And otherwise, if it's not big, one can show easily from this condition here that the map is a Fano fibration. So namely, minus Kx is F ample. It's a relatively ample. So this will be important later. That's of course assuming that you can prove statement C, or in other words, if you have a semi-ample class with this positivity condition. Okay, so first of all, what do we know about this conjecture? Well, basically, what do we know is Kawamata's results and Heikon-McKernan, so for the Néron-Severi part, and then we know for the transcendental case we know only lower dimensional cases. So what we proved with Simeon, now it's already 3 years ago, is that the conjecture holds on surfaces, which is, perhaps surprisingly, it's not totally obvious at all. And we had earlier proved with Yuguang Zhang, well, that was before the conjecture was formulated in these terms, but we proved it up to dimension 3 in the case when alpha is not big. So this would be the case when you expect to have this fan of vibrations, and under the stronger assumption that it's this adjoint of a Kähler class, not just an FM big. Right? So the assumption here is lambda alpha minus kx should be an FM big, but you can strengthen it to Kähler if you want. And under this assumption, under these two conditions, we proved it. And then Andreas Oehring extended this in dimension 3 to the case when alpha is big, so he still under the assumption scalar, or in the Calabi-Yau case when C1 of kx is 0. But as you can see, as far as I can tell, the conjecture as formulated is still open for threefolds, where in some sense it should be accessible. The point is that the main tools for these results are, first of all, the MMP, minimal model program for Kähler threefolds, which is, started by Campana and Peternel, and then more recently completed by Andreas Oehring and Peternel, and also with Campana again for the abundance part. And the other tool is a result of Collins and myself from some years ago on null loci. So I can just give you, if you want, a very brief sketch of the case when n is equal to 2. Here, at least, you don't need the MMP part. So when n is 2, so you want to prove this conjecture here, the part C. So first, you split into two cases. Kx is pseudo-effective or not pseudo-effective. So when Kx is not pseudo-effective, then trivially there are no sections for any powers. So the Kodara dimension is minus infinity. And since we are in 2 dimensions, that implies in particular that H20 is 0, because these are the sections of Kx. And as is well known, this implies on the one hand that X is projective, this is Kodaira, and also it implies that H11 is equal to the Néron-Severi by Hodge decomposition. So in this case, sledgehammer, we can just conclude by base point 3, but of course we are on surfaces, so this base point 3 was probably known a lot earlier. Anyway, this case is done. On the other hand, when Kx is pseudo-effective, then alpha, you see, go back, lambda alpha minus Kx is an FM big. If you move Kx on the other side, you see that lambda alpha is the sum of an FM big plus pseudo-effective, so in particular it's big. So it's also an F because we assume that it's an F. So alpha becomes an FM big. And then you can look at the set of irreducible curves in X which intersect trivially with alpha. And again, I quote here with paper with Collins, but these things are actually, the initial statement in dimension 2 is well known, namely that the set of these curves is finite, and the union of these curves that intersect alpha trivially is exceptional in the sense of Grauert, so it can be contracted. This is well known. And our contribution is that actually you can find the Kähler current on alpha, which is smooth exactly on the complement of these curves. And then the contracted space is a normal analytic surface, which a priori has no reason to be Kähler. However, because of this condition here, that lambda alpha minus Kx is an FM big, one can show using Artin's criterion that this contracted surface actually has rational singularities, and which is special and it's good. So once you have rational singularities, you can show that easily enough that if you push forward this Kähler current on Y, it is still a Kähler current on Y, and you can prove that it has local DD bar potentials, which is not obvious on non-smooth spaces. And once you have local DD bar potentials, this current is only singular at points. because you contracted this finitely many curves, and this can be smoothed out by a classical procedure, and then you can prove that after you smooth it out, you obtain a Kähler metric on Y, and if you put it back, you have a smooth semi-positive form in your class alpha. So the class alpha actually is semi-ample. Okay, so this is a very brief sketch of n equals to 2. And n equals to 3 is a lot harder. You really need to use the full strength of MMP, and even that's not enough. So it's not a formal consequence of MMP. Okay, so, oops. Yeah, so I should say, before I continue on this conjecture, I should basically now, I'm going to mention some more results later and our recent work, but why should one care about this? So of course it's a natural question if you want as a generalization of Kawamata's result, but in fact I claim it has a lot of useful consequences for different problems. So I will mention two problems that I thought about a lot, where this conjecture is extremely relevant. One is the generation of Ricci-flat Kähler metrics, and one is the Kähler-Ricci flow. And one can study this for other, let's say, geometric PDEs, such as the so-called continuity method of Lanab and Tian and others. But I won't go into that. So, so here is the discussion about the Ricci-flat metrics and why this conjecture is relevant. So X now will be Calabi-Yau in the weakest sense, namely Kummer Kähler manifold with the C1 of Kx0 in H11 with real coefficients. So this is the weakest notion of Calabi-Yau, but it's by Yau indeed it's equivalent to the existence of Ricci-flat Kähler metrics. So if for every Kähler metric omega, there's a unique Kähler metric in the same cohomology class which has no Ricci curvature. So if you know, for reference, let's fix one of these Ricci-flat metrics and scale it to have volume 1. And given Neff class alpha, by definition, or remember, it's in the closure of the Kähler cone. So if I add t times omega, this is actually Kähler for all t positive. Here is the picture of the Kähler cone. I, of course, stole this picture from the Mai, but I added this path. The Mai slides, I mean. So you move inside the Kähler cone, and by Yau's theorem now for t strictly positive, you can find a unique Ricci-flat Kähler metric, call it omega t in this class. And if you let t go to 0, they have to degenerate because the class alpha, oh, sorry, I didn't say it. Alpha is Neff, but not Kähler. I take it on the boundary of the cone. So they have to degenerate because they are approaching a point which is not in the Kähler cone. So by definition, since it's in this class, you can write it as alpha plus t omega plus d bar phi t. You can normalize phi, for example, with the maximum to be 0. And the Ricci flatness is equivalent to the Monge-Ampère equation, the volume form of omega t, which is the left-hand side, is proportional to the volume form of your fixed Ricci-flat metric omega. And the proportionality constant is obtained by integrating both sides. And here, unit volume, for me, I remove this n factorial for convenience. So the volume of omega to the n, I just take it to be the integral of omega to the n, which is missing a factorial, but it's okay. I mean, anyway, here the factorials will cancel, but still. You see, this number here is the volume, for me, up to factorials of this Ricci-flat matrix, and it's converging to the self-intersection of the class alpha when t goes to 0. And the main question I've been thinking about for a while is, can we understand the behavior of this Ricci-flat matrix as t goes to 0? So the most well understood case is the non-collapsing case. And the non-collapsing case means that alpha is assumed to be Neff and big, if you want implicitly not Kähler, otherwise the whole theorem is trivial. So you see, sorry, if I go back, when alpha is big, this integral is strictly positive. That means that the total volumes of the Ricci-flat matrix do not go to 0. And that's what I call non-collapsing. So in this case, so it was proved by Esidiu, Gersh, Zeriahi, and then in the special case when it's semi-positive, and then in general by Buxom, Esidiu, Gersh, Zeriahi, that one can solve a Monge-Ampère equation in the limiting class, alpha plus d bar phi 0 to the n equals the obvious limit of the right-hand side when t goes to 0. However, here phi 0 is not smooth, so this Monge-Ampère has to be understood in the non-pluripolar sense, and which I don't have time to define. And what they prove is that you can solve uniquely this equation, and phi 0 is alpha PSH, and crucially they prove that it has minimal singularities. So this is the connection with minimal singularities. And secondly, the connection with the Ricci-flat matrix is that the potentials phi t actually converge to phi 0, in fact, locally smoothly, away from a closed analytic subset, the null locus of alpha, which is simply the union of all irreducible positive dimensional subvarieties where alpha integrates to 0. So we proved that this is the risky closed. There's a closed analytic subset. And away from it, you have extremely nice convergence. And I mean, if you know this EGZ, alpha plus d bar phi 0 is one of the so-called singular Ricci-flat matrix. It is an honest Ricci-flat metric away from this null locus, and it has some singularities there. And Rong and Zhang and proved, and then we extended it, we removed one hypothesis that if globally the Ricci-flat manifolds converging the Gromov-Hausdorff topology, which is as a metric spaces, to some compact metric space ZD, which is nothing but the metric completion of this X minus the null locus together with the EGZ metric, the solution of this Monchampère equation away from the null locus, where it's indeed Ricci-flat and smooth. So this is an open manifold, Ricci-flat, and you view it as a metric space again and take the metric completion. And that's the Gromov-Hausdorff limit. Now, the relation with the conjecture before, well, if the conjecture A holds, then you know that phi 0 is bounded, right? Because phi 0 has minimal singularities and the conjecture applies, right? I mean, I can show it again. Kx is 0, here it drops out. I mean, C1 of Kx drops out. So you just need alpha to be Neff and big. And the conjecture predicts that the part A, so alpha is Neff and big, that's what we assume. So that predicts indeed the phi 0 should be bounded. And if the part B holds, then the class is actually semi-positive. And in this case, EGZ already proved in their paper that phi 0 is continuous. Oh, I think there was modern extra hypothesis, but that was removed. For example, Dinev and Zhang have proved this in this setting here. So the function phi 0 is actually continuous, and you have a uniform convergence of phi t, uniform on all of X, not just locally smoothly away from this subvariety. And furthermore, if conjecture C holds the strongest statement, then I think it should be provable that Z is actually homeomorphic to Y, where Y is the contracted space, right? So if conjecture C holds, that means that alpha is semi-ample, so it's the pullback of a Kähler class on some analytic space Y, Kähler, and this Y should be the Z. And this was proved by Jansong in the case when alpha is in this Néron-Severi group using the base point free theorem as one of the ingredients. So his techniques, which are extensions of work of Donaldson and Sun, probably will apply once you have conjecture C. So you see that the three steps in the conjectures all give you better information than we already know on this theorem. And the canonical example of this result is the case of Kummer K3 surfaces, where you take a torus, say a two-dimensional torus, and mod out by the involution that reflects across the origin. What you obtain is an orbifold with 16 quotient singularities. And this can be resolved by simple blow-ups. So you blow up the 16 points. And what you obtain is classically known to be a K3 surface called Kummer, associated to this torus. And if you take omega y flat Euclidean, say, orbifold metric on y, just coming from a Euclidean metric on the torus, and then alpha, which is the pullback of this orbifold cohomology class to X, is indeed an F and big. And in this case, you see the self-intersection is positive, but it has a non-trivial null locus. The curves, the 16 exception divisors pictured here, of course, intersect trivially with alpha. And in this case, the previous theorem was proved with the different techniques allowed earlier by Kobayashi, Todorov, and again by Lebrun and Singer. So it's a higher dimensional, the theorem is a higher dimensional generalization of this. As for the collapsing case, by that, maybe I go back 1 second. I mean, this setting here, where you have this class on the boundary, which is Neff, but now you assume that it's not big. So the total integral here is 0. So the volume of the Ricci-flat matrix is going to 0. That's what I call collapsing, at least in the volume sense. So if, in other words, what if X is Calabi-Yau and alpha is Neff, but not big? So in this case, the perhaps optimistic conjecture, but I'd be very happy to be proved wrong, to be honest, is if you have a Calabi-Yau and alpha Neff 1-1 class, big or not, but it's only a new conjecture only for the non-big case, then I hope that the current with minimal singularities in the class alpha actually has bounded potentials. If you're feeling even more optimistic, you could extend it from the Calabi-Yau case to the same setting as here, where you just drop here, instead of Neff and big, you would drop the big word, and you would drop B and C out. But I'm not feeling that optimistic, so I will just stick to the Calabi-Yau case here. So what is this conjecture saying? Well, first of all, if alpha is Neff and big, it's just the same as the conjecture A before, of course. But the point is that when alpha is Neff but not big, the analogs, the statements in B and C, namely that alpha is semi-positive or even semi-ample, are both false. So what we proved with Simeon a few years ago is that there are even projective K3 surfaces, or also non-projective if you want, with the Neff 1-1 classes, which you can even pick in the Néron-Severi group if you want, a real Néron-Severi group. They're Neff, they're not big, and they're not semi-positive, so they're not semi-ample either. So means that even though they're Neff, they don't have any smooth semi-positive representative. And these examples I will explain in the next slide. They come from holomorphic dynamics. And in this case, actually, again, alpha has a unique closed positive current. So there is a unique alpha PSH function, modulo constants, phi min, which is a Hölder regular, C gamma for some gamma positive, but it's not smooth. That's what we proved. And also the X omega t, if we look at the Ricci-flat matrix in these K3 surfaces approaching that class, in Gromov-Hausdorff, actually, you just get a point. So the diameter just shrinks to 0. So this is just to say that one has to be a little careful when trying to generalize naively conjectures. If you just try with the most naive statement, the alpha should be semi-ample, this is totally false. And maybe I should ask that for Calabi-Yau's, the statement that a Neff line bundle should be semi-ample or should be numerically equivalent to a semi-ample line bundle in the projective case is a conjecture which is expected to be true. And a lot of work has been done there. It's known in some cases, but it's not proved in general. So in other words, there is some, you can say, extension or not really of the base point free theorem for Calabi-Yau, expected conjectural statement. But if you just translate it to 1-1 classes, it's just false. So a word of caution. And on the other hand, before I talk about these examples, let me just say that if alpha is Neff not big, but you do assume that it's semi-ample, so namely that it is the pullback of a Kähler class from some lower dimensional space Y, then the behavior of the Ricci-flat matrix is much nicer. And actually, I've been working on this a lot with a lot of people. As you can see, a partial list of recent papers on that. So there's a huge story there. The point is, this is all under the assumption that the Neff class is semi-ample. So it comes from a fibration type map pullback from a lower dimensional space. Okay, so maybe this is now we're getting to the more recent work with Simeon, but this is still the previous page, the previous example. So these examples are the 2-2-2 K3 surfaces. So they were discussed by Barry Mazur, who was following suggestion by Joe Silverman in the 90s. So you look at the hypersurface in P1 cross P1 cross P1, which is a zero locus of 1 multi-homogeneous polynomial of degree 2-2-2 and sufficiently generic. So these are all K3 surfaces, and you can project onto P1 cross P1 in 3 different ways by dropping one of the factors. Each of these projections is, of course, a ramified 2-to-1 cover because of the degree 2-to-2. So you have covering involutions, sigma 1, sigma 2, sigma 3 of X. And the they are involutions, but if you compose them, sigma 1 compose sigma 2 compose sigma 3, this becomes an automorphism of X, which has infinite order and in fact has a chaotic behavior. So this picture, this is just the picture of the real points of one of these 2, 2, 2 for a suitable choice of the polynomial. So it has this kind of shape over the reals. And this is Kurt McMullen's picture of an orbit. Oh, sorry, there's an orbit, kind of a dust. The dots, the red dots are an orbit of iteration of T, and the blue stuff is a stable manifold of T. So the behavior of these iterations of this T is quite chaotic. And here is the picture of is a picture of a section of the Néron-Severi, of the ample cone in the Néron-Severi group. So if you choose P generic, the Picard number is 3. So H11 and not H1, and S Néron-Severi is rank 3, and S of XR is R3. Inside R3, you look at the hyperboloid of classes with volume 1. So that's a 2-dimensional disk. Here it's a Poincaré model, and so the boundary of this disk are classes on the boundary of the ample cone, and then this standard, you call it paving, hyperbolic paving here is simply the action of T in cohomology. So if you pull back 1, classes, there is a fundamental domain, which is this ideal triangle here. And when you apply, it's the action of sigma 1, sigma 2, sigma 3. It's the action of the automorphism group. Sigma 1 flips this triangle into here, sigma 2 into here, sigma 3 into here. And if you apply the full automorphism group, you get this hyperbolic paving of the disk. These examples are not Kummer if P is generic. And as I said, there is these involutions generate a Z mod 2, and their free product is a subgroup of the automorphism of X. And in general, for P generic, it's actually equal. Okay, so what's that to do with my MF classes? So if you have this automorphism T, and you take a Ricci-flat Kähler metric omega on your K3, then one can compute that the spectral radius of the pullback on H11 on this K3 is strictly bigger than 1, call it lambda. And this actually is the condition of chaos, according to a famous result of Gromov and Yomdin. And then if you pull back, so if you take iterates of T and pull back your Kähler class, and each time you pull back, you also rescale by this larger spectral radius, then these classes pass to the limit. Essentially, by linear algebra, you can see that the limit is an eigenvector, it's an eigenclass. This class is non-trivial, it's not the 0 class. And Cantat showed that, first of all, this class is Neff, that's obvious. It's not big, that's also pretty clear because it's on the boundary of the light cone. Actually, in these examples, it lies in the real Néron-Severi group. And more importantly, he proved that it contains a unique closed positive current that you can call eta. And this current, therefore, must be itself expanded. So you can pull back closed positive 1, currents under automorphisms. And this pullback of eta is lambda times eta. So eta, in other words, you can write it as alpha plus d bar phi min. Min is the unique closed positive current. And Dean Sibony proved that phi min is actually Hölder continuous. I mean, Cantat had proved earlier that it's a continuous. It's in fact a Hölder. But what we proved using a theorem of Cantat and Dupont, and which we later reproved and extended ourselves, is that this phi min cannot be smooth. Basically, our theorem is a lot stronger than that, but one simple way to state a consequence of it is that if this were smooth, then there is a dynamical rigidity that implies that X must be Kummer. And as I said, this K3 is not Kummer. So there are also other non-projective examples where you can use earlier automorphisms constructed by Kurt McMullen. So yeah, here is the
why the pullback of alpha by T is proportional to alpha.
This one, right?
Yes. Yeah.
Exactly, because you rescale by the spectral radius. So if you can just think in terms of matrices, right? There's a matrix acting on this I don't know, R20, and if you divide every time by the spectral radius of this matrix, eventually you always have to converge to an eigenvector. I forgot what it's called, Perron-Frobenius maybe. Perron-Frobenius theorem should imply this.
Okay.
Yeah. It's essentially linear algebra. Yeah, but it's if you want the proof, it's in Cantara's paper or thesis, both. Yeah.
Okay.
Yeah, it's not that hard, but yes, maybe not entirely obvious. The point is alpha also is not trivial. I mean, easily you can get the zero if you put a larger lambda. But you see, if you take the spectral radius exactly, you get a non-trivial class, not the zero class. Yes, I mean the zero class would also be an eigenvector, but it would not be interesting at all.
Okay.
Yes. Yeah. So here is the recent stuff we've been doing. Basically, I would like to have at least a basic understanding of Neff classes on K3 surfaces. So after all, K3s are two-dimensional Calabi-Yaus. They should be extremely simple in some sense, but that's of course not the case at all. They're two-dimensional, so how hard can it be? Well, so here it is. So first of all, so X is going to be now a K3. It does not have to be projective, and alpha will be, say, an arbitrary Neff11 class. These first bullet points, so the first one is essentially the proof I described earlier of the conjecture that if alpha is also big, then alpha is semi-ample. I actually told you the argument earlier. So if alpha is Neff and big, then it's as nice as you can hope for. And this is classical, actually. I mean, I put our names, but it's essentially algebraic geometry. If alpha is not big, and if you look at the half line spanned by alpha, it contains some rational point, then alpha is also, again, semi-ample. This is, again, essentially standard K3 surface geometry. However, Sibony and Verbitsky, unpublished still, but you can find some notes of a talk by Verbitsky. They prove that if alpha is, again, F, but not big, and this line, half line, has no rational points, then they prove that alpha contains a unique closed positive current. So again, the phi mean is essentially unique up to a constant. And in this last case, therefore, is the one that one needs to understand. What is the regularity of phi mean? So if you go back to the optimistic conjecture, it says that they should be bounded. And in general, surprisingly enough, this is totally open, so completely unknown. And as the previous examples show you, this phi mean will not be smooth. So it's not smooth in general, but I'm hoping that it's bounded. And here is the recent theorem, which is still we're finishing to write up, so it's not yet available. So assume that it is for the projective case. So it answers the optimistic conjecture under some assumptions, but it answers and it gives a lot more information. If you have a projective K3, assume rank of Picard is at least 3. This one is harmless because Picard 1 and 2 are kind of stupid. And assume no -2 curves, which probably can be removed, but it's there just for safety. And there's also an extra technical assumption about genericity, which we hope can be removed, so I didn't even write it. And assume, let alpha be an F class, which is in the Norodom-Severi group. So it's a class of an R divisor, Neff, but not Kähler. Then there is a phi which is continuous on X, so better than bounded, such that alpha plus TD bar phi is semi-positive. So in particular, optimistic conjecture holds for these classes because phi is in fact continuous, phi min. And also, even better, you can choose phi to vary continuously. So as you change alpha on the boundary of this ample cone, the corresponding phis will change, can be chosen to vary continuously in the uniform topology. So you have actually somehow a canonical continuous family of representatives of closed positive currents for all these boundary classes under these assumptions. And so in particular, this applies to the classes here of Sibony Verbitsky, right? The ones that are truly irrational, they have a unique closed positive current, and by this result, under these assumptions, this phi mean is continuous there. And we believe that, so remember that there are the ones coming from dynamics, which are just a Holder continuous, sorry, which are even better, they're Holder continuous. We believe that in general, one cannot pick phi to be Holder continuous for arbitrary classes. So somehow C0 should be sort of optimal. And if you are in this truly irrational case, then the Ricci-flat matrix will Gromov-Hausdorff converge to a point. Again, the same behavior as in this dynamical setting. Yeah. So as I said, we're kind of writing this up because also this is only a very small sample of what we actually prove, and there's a lot of other stuff there, but this is the one that I can easily present here. And the very rough idea, like 2 words about the proof here. So we need to restrict to projective and Néron-Severi because we are going to apply the so-called Kawamata-Morrison cone conjecture, which is a conjecture for Calabi-Yau's, but for K3 surfaces is an old theorem of Sturck. And it tells you exactly that you have a picture like this. So if you look at the ample cone of a projective K3, again, you can just look at the classes with volume 1, which gives you a model of projective of hyperbolic space of possibly higher dimension, right? Of Picard -1 dimension. Then you can find a fundamental domain, which is a rational polyhedral, like this triangle here, such that under the action of the automorphism group, this fundamental domain covers the whole Kähler cone. Okay, so you have a generalization of this picture here. The Poincaré disk becomes a hyperbolic space of dimension Picard -1. You have a tiling or paving of the hyperbolic space given by this Kawamata-Morrison cone conjecture. And then the idea is if you want to reach a boundary point here, you can find a suitable word in the generators of the automorphism group. You see that starting from a Kähler class somewhere in the fundamental domain and applying this sequence of automorphisms, these words, they will take you right there. That's from this picture here. And now you need to do some careful estimates, especially it's easiest to work with a quotient of this Poincaré module automorphism. That's a hyperbolic manifold with cusps, and you have to do some estimates to see how the Kähler potential grows under this when you apply these words in automorphisms, and eventually you can prove that you have a continuous limiting potential. So that's the 2 words idea. Okay, so I think my time is up. Sorry, so I had some few more slides about the Kähler-Ricci flow, but only if there's some people interested, I can show you I can say a little bit about it later in the question in the Q&A. But otherwise, I think I'll stop here. And thank you very much.
Thank you very much for the talk. And now it's time for questions and remarks. Any questions?
So could you say something about the Kähler-Ricci flow?
Yeah, I can say a few words. Let me just go briefly. So basically, you run the Kähler-Ricci flow. Now it's not Calabi-Yau anymore, and you know the maximal existence time, which is infinite if Kx is an F, this kind of minimal condition. And the point is that the conjecture, not the optimistic, the other conjecture, the main conjecture, would have consequences for both the finite time and infinite time singularities. So to really make it brief, if you have a finite time singularity, that's when the canonical boundary is not an F, then you have a limiting cohomology class of the flow, which I call alpha. And this exactly is one of the classes that satisfy the conjecture. So namely, you see by the way the class is exactly the adjoint of a Kähler class. So it's even better than the conjecture. The conjecture was only assuming there is an Fn big. So this is an adjoint of a Kähler class. And in fact, that's a characterization of the classes that you hit in finite time by the Kähler-Ricci flow. Right? So an F class on the boundary of the Kähler cone can be hit by a Kähler-Ricci flow in finite time if and only if it satisfies like lambda alpha minus Kx is scalar for some lambda positive. Okay, so that condition characterizes the finite time singularity classes of the flow. So these are an F, and if you believe the conjecture with Simeon, then these classes should be all semi-ample. So you should always have these contraction maps. And then if, as I said, if the limiting class is big, this will be bimeromorphic, in which case you can hope to do some surgery. And this has been done in the simplest type of contractions by Song and Weinkoff. Maybe more interestingly, if it's not big, as I said, you get one of these Fano fibrations, and if you could, therefore, if you could prove the optimistic, no, the main conjecture with Simeon, actually these two conjectures would follow by work I did with Yuguan Zhang. Namely, you can characterize which manifolds, Kähler manifolds, have a finite time collapsing solution of the Kähler-Ricci flow. They will be exactly the ones that admit a Fano fibration. And you can characterize when you have finite time extinction, which means you have finite time singularity and the diameter is going to 0. Or Gromov-Hausdorff, you have a point. That would be if and only if X is Fano and the initial class is proportional to the anti-canonical, so the standard case. So these two conjectures both would follow from the conjecture with Simeon. So you can see the paper with the Zhang that we wrote about this. And yeah, this one was explicitly formulated by Tian quite a few years ago. And for infinite time, still for finite time, it would also imply a conjecture of Zhou Zhang, that if you have a finite time singularity, you actually have a uniform bound for the Kähler potential along the flow all the way up to the singularity. Because again, Zhou Zhang in a special case, and then with Collins in general, we proved that as a finite time singularity, you can always take a limit in the L1, say, to a quasi-PSH function in the limiting class, and we proved that this always has minima singularities. So even the part A of the conjecture would imply that the phi is bounded, and one can easily prove that then along the flow is uniformly bounded. So you would resolve already these 3 open problems about finite time, and at infinite time, maybe infinite time is not a direct, it's not a consequence of the conjecture, but maybe I can just show this as a kind of motivation conjecture for people. So if you have a infinite time solution, so canonical boundary is Nef, and assume that the Kodaira dimension is strictly less than n, so it's not big, Nef and not big, and you run the normalized Kähler-Ricci flow, like this minus Ricci minus omega, then the potential in the normalized flow will converge, conjecturally should converge, at least in L1, without subsequences. And this will give you a closed positive current in the limiting class, which is the canonical class. So you would obtain a singular metric on Kx as the limit of all possible Kähler-Ricci flows on X. The limiting singular metric on Kx should be always the same. It should be canonical. So if you run the Kähler-Ricci flow for infinite time, you should always converge weakly to the same singular metric on Kx, and this should have minima singularities on Kx. And if you're even more optimistic, it should have bounded potentials, and I mean even more. In practice, in all the examples we know, it's even continuous. And this is again totally open, but possibly some parts of this conjecture are easy, namely to obtain a limit without subsequences and to prove that it's independent of omega 0. Maybe it's not so hard. Minima singularities, who knows? Maybe that's also not so hard. And the boundedness is probably quite hard. But yeah, so this is not a direct consequence of the other conjecture, but it's in the same spirit. Okay, yeah, sorry, it's a very short summary, but
Thanks.
Yeah.
Thanks. And some other questions?
Yeah. So I have another question. So if in the case 1x is a compact Kähler surface, but not necessarily K3. So for the so-called we also prove some kind of union. Could we also prove some uniqueness results, which generalize the results of Sigoni Verbitsky?
Oh, you mean me or you?
Yeah.
Do I know?
So do you know? Or,
I see.
So
I see.
for that, so for their proof, they really. So for their proof, they really need that X is K3.
Yeah, that's a good question. Yes, for their proof, yes, but yeah, yeah, I have to think about it. Yes, I have to think about it. I mean, they use some, you can say, standard facts about the automorphism group of K3s, but I think you can probably extract some more abstract statement. So with some conditions on the action of out X, and then their argument applies. There is definitely some quite non-trivial input in their theorem, which comes from homogeneous dynamics. So stuff like Ratner's theorem must be used, and that also has hypotheses that one has to check are satisfied. So, but yes, basically, yes, it will definitely apply in more generality for sure. But I didn't think what's the optimal statement. Yeah. You can find a sketch in if you Google, or actually either Google rigid currents, Verbitsky rigid currents. You can find his slides, and he has a sketch. But yes, we also plan to put the sketch in our paper when it comes out. So because Sibony Verbitsky, I haven't seen it yet. I think that it's a little delayed. Maybe they're trying to prove some more stuff. So we will put. It will also be in our paper, their proof. But yes, yeah. The general statement, yes, it's related. You need to check some conditions on this homogeneous dynamics, and then they happen to hold for K3, and they will hold in some other cases, but not in general. Yeah. So okay, it's a good question. Let me think if we can formulate a more applicable criterion. Yeah.
But so in their result, so they could not exclude that alpha contains some exceptional -2 curves.
Yeah. That's right. The -2 curve, yes, only makes things a little annoying. You have to pass to some finite index subgroups of the automorphism. But I think it's probably just a technical assumption here. I think you should be able to just remove it. Maybe we will try to remove it before we finish the paper. Yeah, it's just those create the technicalities with the action of the automorphism group. You know, this what are they called? Chambers and walls, walls given by the -2 curves in H11 of the K3. And if you don't have -2 curves, it's the picture is easier. But yeah. I don't think they need it in their argument. Yeah.
Okay. I see. Thank you.
Yeah. But yes, in general, what is the regularity of this phi mean? It's not clear. As I said, there are examples where it's not smooth. There are examples where it's Holter continuous, and in many cases it's at least continuous. But in general, we don't know. And this is on K3, so it should be kind of classical, but it's not at all. Yeah.
Okay, thank you.
Yeah, you're welcome.
Hello, Valentino. This is Jean-Pierre Demailly.
Yes, hi.
You hear me?
Yes, I hear you. Yes.
So I have a general question. Maybe it's a stupid question. I don't know. Do you believe it could be possible to prove that the potential has at least 0 low numbers in the situation of your conjecture? So you assume that the class is nef, that alpha minus C1 of Kx is big enough, and then maybe by some iteration technique like in Hughes' proof of invariance of Fleury-Denerat, you might reach that the low numbers are always 0. Is this known, or?
That's a good question, right? Yeah. Yeah, that's a very good question, right? Of course, assuming that alpha itself is not big, otherwise it's fine. Yes.
Of course, if it's big, you know.
Then it's okay. Yeah. Yeah, I haven't thought about it. Right. So you are saying put an even weaker statement here. Yes, before
Yeah,
A.
yeah,
Yes.
so it will be even before A. So,
Before A. Yes.
Yeah.
Yes. Yeah. I mean, on the spot, I don't think it's known, but maybe I'm missing some. Maybe I'm missing something. But
because it looks a simpler statement, because you need only some weak approximations somehow, and just like when you assume alpha big enough, you can go to some supremum technique.
Yeah.
Reach
Yeah.
L2 something like this.
Right. Yeah. It's not clear. Yeah, it's not clear to me. Yeah. I'll think about it. If I find a simple answer, I'll let you know. But
Okay.
yeah, otherwise, I'm happy to add it to the list, of course. Yeah. Because if it's not trivial, then one at least should try to prove that first, right? If one can't prove the simpler, I would say, weaker statement. Yeah. Thank you. Yes, that's a good point. That's a good point. Yeah. I mean, I guess, and yeah, one can probably ask the same here, right, in the optimistic one as well.
That would be already good, I believe.
Yeah.
I don't think it's known either.
Yeah, but as I said, this is optimistic, so it has a bigger, in other words, it has a bigger chance of being wrong than the other one, I would say. Just because the strengthening of this one with semi-positive turned out to be false. So one should
also, another question: have you thought of a possible counterexample to your conjecture, in case you would have, instead of a morphism x to y, some sort of foliation with non-compact leaves instead? Might such a situation happen, which would somehow provide something that is, say, with a smooth potential, but the leaves are actually dense.
Right.
Some Hilbert modular surfaces, of course, surfaces, you prove it, but something like this in higher dimension.
Yeah, I have to think about it, right? Because yes, right. So for example, yes, there's even the kind of trivial example of tori, right? But there is indeed kx would be 0 here. So for this conjecture, that doesn't work because alpha itself would be big, and then on a torus that has to be Kähler. But yes, yeah, that's right. If you have these foliations that do not give you vibrations, yes, that can give counterexamples to these kind of statements. Yeah, I mean, right. Basically, my feeling is that it shouldn't give a counterexample to this because of this bigness assumption here. Right? And on the other hand, in the optimistic one, that can definitely happen. Like for example, these dynamical ones, they have a even weaker than foliation. They have a laminated structure. This what is it? This eta, right? This eta, the dynamical green current. Yeah. It has this extremely ugly laminated structure, so even weaker than foliation. And indeed, there you go. That is not semi-positive or semi-ample. So somehow, yes, that's already in the spirit of your question, but it should not. Yeah, so definitely that can happen here, right? Without bigness, without any bigness anywhere. But it should not. It shouldn't. I mean, I'm hoping it shouldn't happen here because of this assumption. But yeah, maybe it's quite possible the conjecture is false. Yes, indeed. I mean, there is some evidence. I said this lower dimensional cases, but you never know. I mean, yeah, right. One can of course strengthen it to Kähler. I mean, that's the other thing, that in dimension 3, one needs this Kähler instead of just Neff and big. So one can also just put that as the assumption, maybe, which is, as I said, related to the Ricci flow. That those are the classes that you obtain by Kähler Ricci flow, and that could make things slightly better. But,
okay, yeah. Thank you, Valentino.
Thank you so much for coming.
Very good talk.
Thank you.
Thanks. Some other questions? Okay, there seems to be no more questions. So then thank you very much for the talk. And
Thank you.
talk.
Thank you all for coming. Yes. Yeah, I wish we could have met in person, but
Yeah, I hope so after the pandemic.
yeah, such is the time.